So, hello. In today's lecture, we are going to study coupled oscillators, and let us first understand how to solve coupled differential equations, or in other words, how to decouple a differential equation. Okay. Let us start with first something regarding coupled differential equations. So, I'll not go with a very formal definition, but I will start with saying that if two functions, if two functions, uh, let's say x as a function of t and y as a function of t are related by a pair of differential equation, are related by a pair of differential equation, we'll say they are uh, constituting a system of equation which you can say as a coupled differential equation, a pair of differential equations. Okay, so first thing this. Okay, now next thing that one needs to understand is the how to understand how to solve such kind of differential equations, or what is so special about these differential equations. And you'll find that more often in your coupled oscillators, okay, where you have like uh, two masses arranged attached to three springs or such cases, okay, you'll find that you will encounter something called as coupled differential equations. And in order to find some physically reliable solutions, one needs to understand the um, I guess the solutions for these coupled differential equations. So, for example, let us take, for example, two equations which I'm giving: 2x double dot plus omega square 5x minus 3y equal to 0, and you have 2y double dot plus omega square, and then you have this 5y minus 3x equal to 0. So this is your equation number 1. This is your equation number 2. How to solve them? How to solve them? Okay. So there are two methods which I'm going to illustrate in this lecture, and then we'll see one case, and then we'll see quite many in lectures to come. Like we'll take around 2 to 3 lectures, or probably 4 lectures on this coupled differential equations and coupled oscillators. Okay. So for example, if this is the example that I'm giving, and you can see that both of the equations have x and y. So x as a function of time, you will get here also, and here you have a differential equation which has a y as a function of time, the double derivative, and y appears here, x appears here. So what can be two ways to solve it? Although when we'll be doing Lagrangian formalism of oscillations, we'll be doing the same sort of problems there also, but our approach would change. Okay, but right now let us take an easier approach to do the same. So one of the ways can be to find if linear combinations, if linear combination of x and y can work. Okay, so what you can do from the very much like you can observe that if I add 1 and 2, if I add 1 and 2, what will happen? This will be like omega square, and this 5x minus 3x will give you 2x, and then this would give you plus 2y. And so overall, you'll get 0. And you can see that there is a differential equation in x plus y. You can say 1x, there is a differential equation x plus y. And you can say that this particular differential equation satisfies the differential equation for free oscillations. So if you place x plus y is equal to z, you're getting a differential equation which is z double dot plus omega square z equal to 0. And you can write the solution as z equals to some a1 cos of omega t plus 5. And instead you can write x plus y is equals to a1 cos of omega t plus 5. I hope it is clear. And the second one, you can see if you just try to subtract 2 from 1. try to subtract 2 from 1. So what you'll get, you'll simply get x double dot minus y double dot plus, you have, I think, plus 5x minus minus. So I think if you solve it, so you'll get 4 omega square, and then you'll get x double dot minus y double dot. This is how you're going to get. So in this differential equation also, you can write this is a differential equation in x minus y, and clearly you can write that your x minus y is some a2 cos 2 omega t plus y2. Is that clear or not? Okay. So you can see that we've arrived at a solution by just doing one thing, by trying to write the solution. Like we've just played with mathematics, and we've just added it up and subtracted it. And we know that as we add, we are getting a differential equations, which is quite similar to one we get for the free oscillations, right? So this is how these are the solutions that we're getting. And if you want to obtain the solution in x and y, what we can do, x as a function of t can obviously be written as some a1 cos omega t plus phi 1 plus a2 cos 2 omega t plus phi 2 divided by 2. And similarly, yt can be written as a1 by 2 cos omega t plus phi 1 minus a2 upon 2 cos omega t plus phi 2. So this is one of the ways in which you can decouple your coupled differential equations. You can decouple your coupled differential equation. Is that clear to you? What one needs to see, that this differential equation, which is in x minus y and x plus y. So you can see that this coordinate is oscillating with the frequency, one pure frequency, that is omega. So there is a one pure frequency, which is omega here, and there is a one pure frequency, 2 omega here. Is that clear? Frequency 2 omega. Okay. So you can expect a very nice sinusoidal sort of behavior for x plus y and x minus y. These two functions are called as normal coordinates. These are called as your normal coordinates, because see, you can clearly see that x and y are behaving in quite unpleasant manner. Like they're having it is a linear combination of two sinusoidal solutions, one oscillating with 2 omega, another oscillating with omega. But however, if you see that x plus y, it oscillates with the pure frequency, and x minus y, it again oscillates with the pure frequency. So you have a know-how of two independent motions which are executing with the pure frequency, omega and 2 omega. So here you have this linear combination of two different sinusoidal functions. Here you do not have. So x plus y is going to oscillate this particular coordinate, or this particular mode you can see is oscillating with some 2 omega. And this is again oscillating with one other pure frequency, which is, this is with 2 omega and this is with omega. Is that clear? Another way, which this quite like the structure wise, you'll see the same thing when you are going to do Lagrangian also. But right now I'm not doing Lagrangian. So right now, an easier approach that I'm taking is, the second approach can be to assume some trial solution. Assume some trial solution. So what can be a trial solution? A trial solution can be of the form, let's say x as a function of t, you just assume it as a e to the power iota alpha t, and you assume y as a function of t as b e to the power iota alpha t. Let's say these two are the solution. And for convenience, let us write in the manner of a matrix, like matrix form. I write these system of equation in terms of this. Is that clear? Now, okay. Now, what can be seen is, if I replace these x as a function of t and y as a function of t, what I'll get? So if I replace in my what was my differential equation? I'm writing it here. It was 2x double dot plus 5y Sorry, it was, just give me a minute, it was 5x, sorry.
Omega square into 5x minus 3y.
5x minus 3y it was here. And so let us replace the solution. So if I replace the solution, what I'll get? Minus 2a alpha square, and then I will get plus 5a omega square, and then I will get minus 3b omega square equal to 0. This is my equation number 1. And then I have an equation number 2, which suggests me that minus 2b alpha square, and then I will have plus 5b omega square, and then I will have minus 3a omega square. Is that clear? So these two differential equations. So the answer is that one of the ways that I've taught you in order to decouple a couple differential equation, this may not often, like quite often, it may not work also, because it's like here it was quite easy to see that there can be two different linear combination which can move with a pure frequency. Okay, but not always you can find that that you are able to do certain kind of maneuvering in the exam or otherwise also. So what you can do, you can assume some trial solution. And why I'm assuming a trial solution? I'm assuming a trial solution of an oscillatory form. So let me assume a solution of a e ki power iota alpha t, and y as a function of t as b e ki power iota alpha t. And what I get this thing from the differential equations, because e ki power iota alpha t is not going to be 0. So the remaining terms are 0. Is that clear? And if I write all these things in matrix form, so let me write all these things in matrix form. This will be not 2a, sorry. This will be like minus 2 alpha square, and then you have this 5 omega square, and then you have minus 3 omega square, and then you have minus 2 alpha square, and then you have plus 5 omega square, and then you have minus 3 omega square. Is that clear? And then you have a and b equal to 0. Clearly, you can see this is a homogeneous equation, isn't it? This is a homogeneous equation. And one of the solution which is quite evident is a trivial solution. Is a trivial solution, that is a equal to 0 and b equal to 0. If a and b are both zeros, these solutions are called as trivial solution. Quite often you will find in physics that these solutions corresponds to your object at rest. Okay, so it is not going to tell you anything about dynamics, because anyway, if a is something, then only you can say that x is evolving with respect to time, and if b is some non-zero value, only then you can say that y is evolving with respect to time. Okay, so if it so happens that a is 0 and b is 0, then obviously this trivial solution is mathematically maybe significant, but physically it's not quite significant, but because it is going to only tell you about that the system is in rest. Okay, so leaving behind these things, what we are interested in physics, we are interested in finding the non-trivial solutions to it. So given this, so for example, if I have this homogeneous system of equation with ax is equal to 0, and I want to find this eigenvector x, or you can, sorry, if I want to find this eigenvector, if I want to find this x, what I need to do is I have to multiply both of the sides by a inverse. I have to multiply both sides by, or I have to operate on both sides a inverse. And if I operate on both sides a inverse, only then I can get back the solution. Is that clear? Okay, but the problem with the solution is that solution would be trivial. Is that clear? If I apply a inverse on both ends, I'll have only trivial solution. However, in physics, we are not interested in finding the trivial solution. We are interested in finding non-trivial solution. By which I mean that if a inverse existed, then what I can do, I can find a I can find a trivial solution. Okay, is that clear? Not clear? कहाँ चली गई सब वापस गायब हो गई अल्पना ठीक है सो देखो ए एक्स इक्वल टू 0 है अगर ए इनवर्स एग्जिस्ट करता है तो ए इनवर्स दोनों साइड मल्टीप्लाई करके एक्स को हम 0 0 इन्वॉल्व कर सकते हैं देखो ना ए इनवर्स ऑपरेट यू विल गेट 0 0 ऑपरेट ए इनवर्स हियर ऑपरेट ए इनवर्स हियर
यस सर
okay this is 0 is 0 0 so a point is this ki in any case if I have this thing if my matrix is क्या कह सकते हैं, if my matrix is sort of invertible, this is invertible, then I may get a trivial solution. However, I don't need a trivial solution. So for a homogeneous equation, A and B will have a non-trivial solution. A non-trivial solution only if your matrix is non-invertible. So here I'm writing matrix A. इसको ऐसे लिखो, फिर M लिख दो एक काम, और X को लिख दो A लिखो. So this is your M and this is, let's say, your X. So if M inverse exists, then M inverse operating on both ends will give you a trivial solution. However, understand, we are not interested in finding a trivial solution to it. Okay, so we want to find non-trivial solution. Okay, now the question about invertibility would involve obviously finding cofactors and finding transpose, and then dividing the adjoint by transpose. Dividing the adjoint by determinant. So that is a very long and tedious process. Let us try to take a shortcut. Okay, and what that shortcut would be? That shortcut would be that an inverse will exist. An inverse will exist only if your inverse of M would only exist if your determinant is non-zero. Is that clear? Because your matrix should be a determinant should be a non-singular one. Because if your determinant is singular, that is, if determinant is zero, then inverse of M is not possible. Is that clear? If determinant is non-zero. However, if inverse would exist, then the solution will have an inverse trivial solution, which we are not interested in. So what does it imply? It implies that a non-trivial solution will exist only if determinant is zero. Okay, so if determinant of M is zero, then a non-trivial solution will exist. Because if determinant of this is non-zero, then M inverse would exist, and if M inverse would exist, operating M inverse would give you a trivial solution. So that will not give you any sort of physically reliable solution. So what you have to do is, you have to see that for obtaining non-trivial solution, your determinant of M must be equal to zero, and which would yield you -2 alpha square, and then I had some 5 omega square, and then I had -3 omega square, and then I had, I think, minus again 3 omega square, and then I had again -2 alpha square, and then I had +5 omega square equals to 0. Is that clear or not clear? वापस बोलूं, पूछ लो एक बार. See, this is the system of equation mx equal to 0. This is a homogeneous equation. If M has an inverse, then M inverse mx is equal to M inverse 0. So x equal to 0. So that implies you will get a trivial solution. Now, we want that trivial solution should not be there. So what we want somehow that M inverse should not exist. Now understand, M inverse would always exist if the determinant of F is non-zero. For a non-trivial solution to exist, you should have a condition that inverse should not exist. That implies your determinant should be 0. So if your determinant M is 0, then its inverse would not exist. So therefore, it will yield you some non-trivial solutions. Is that clear or not clear? Rajat, Pragya, Alpna.
Yes, मैट्रिक्स गलत लिखी है या फिर यही होगी?
-2 alpha square plus 5 omega square. सॉरी, मेरी गलती. इसको जस्ट रिवर्ट करना पड़ेगा. ये वाला इधर आएगा और ये वाला इधर चल जाएगा, राइट? मेरी गलती. बिकॉज सी, इधर क्या था, -2 alpha square plus 5 b omega square and then -3 omega square. तो यहाँ पर क्या था, यहाँ पे आई थिंक देखो ना, यहाँ पर क्या है, दिस इज b हियर ना, तो b तो इधर आया ना, सॉरी. सो b इधर है, तो आई थिंक दिस विल बी -2 alpha square and then this will be 5 omega square, and here it will be 3 minus omega square. Is that clear? Sorry, मतलब ये a वाला portion you have to write here. Okay, so that is clear. So if this is the case, then try to find what will be the omega value. So you will get a biquadratic equation. So multiply this. This is 5. This is 4 alpha ki power 4. And this is minus 5 like minus 10 minus 20 minus 20 alpha square and then omega square. And then you have plus like 15 25 from here, 9 minus ho jayenge to kitna ho jayega? I think it will be 16, right? 16 omega ki power 4 equal to 0. And one can clearly see that this is a biquadratic differential equation, biquadratic equation. So you can take your alpha square as y and you can try to solve it. And once you solve it, I hope you'll get an answer as alpha is equal to plus minus, solve it fatafat se. If I know, answer would be omega, and another would be alpha equal to plus minus 2 omega. This is something that I'm leaving it to you. So alpha, you will get plus minus omega and plus minus 2 omega. This is something that you can check on your answer. If I replace alpha equals to omega, let me see how does what is the relationship between A and B. So what is the relationship between A and B? Let us find. So this will be like minus 2 omega square plus 5 omega square and minus 3 omega square. Here you will have minus 3 omega square, and again you will have minus 2 omega square plus 5 omega square, and then you have this A and B here equal to 0. This will yield you, this is like minus 3, so plus 3, this will yield you A equal to B. This will yield you A equal to B. Try this. So this is 3 omega square minus 3 omega square minus 3 omega square 3 omega square. This will yield you A equal to B. And similarly, if you try to find corresponding to alpha equal to plus minus 2 omega, you will get A is equal to minus B. So at times in the theory of equations, a theory of oscillation, this is called as your symmetric mode. This is called as your anti-symmetric, your out of phase mode. This is your symmetric, and these we'll study later on. But right now I'm just doing mathematics part of it. Is that clear? Or is that not clear? So what we are doing, wo to nahi bhul gaye tum. So we are doing method number 2 for finding the suitable method for decoupling our coupled differential equations. Okay, so assume that there is some trial solution, that is x as a function of t as a e ki power iota alpha t, y is equal to b e ki power iota alpha t, and we've got a system of a homogeneous equations. And for this, we know that if M inverse would exist, then we'll get a trivial solution, and we do not want a trivial solution. So we want that M inverse should not exist, which implies that your determinant must be 0. And if you end up finding your determinant to be 0, then obviously you'll get some two results. That is, alpha is equal to plus minus omega, and alpha is equal to plus minus 2 omega. And what is alpha? Remember, the alpha is the exponent here. Is that clear? So now, if I use all these things in my solution part, so what is my solution? So my solution was xy was equal to a and b. Okay, so I'll write 4 solutions. So I have 4 solutions corresponding to this. So for alpha equal to omega, your a was equal to b. For alpha equal to minus omega, your a again was equal to b. For alpha equals to 2 omega, your a was equal to minus b. And for alpha equals to again 2 omega, minus 2 omega, your a was equal to minus b. Is that clear? So you have 4 different categories of solution for corresponding alpha. You have these a and b's. And once you know that your a and b's are there, so what you can do, you can take this as a equal to b equal to some, let's say, some constant. Okay, let us take it as some constant. Okay, let us take this as some constant, let's say a1, and let us take this this as a constant, let's say a2, and let us take this as a3, and let us take this as a4. So what I'll do, I'll write a1 1 e ki power iota omega t plus a2. This is also solution 1 e ki power minus iota omega t. Then a3 is 1 minus 1, and you have e ki power iota 2 omega t, and then you have a4, and that is 1 minus 1 e ki power iota 2 omega t. So this is your solution for x and y. Is that clear? Or is that not clear? Okay, so now in order to simplify, what people do, they try to write this a1 as some factor. जैसे हम नहीं करते थे हमारे trigonometry के अंदर कि अगर a cos omega t plus b sin omega t दे रखा होता था, तो we used to write it as some a cos phi and this as a sin phi, ऐसा कुछ. Okay, so ऐसे कुछ यहाँ करेंगे. Let us try to write a1 and a2 in a way that it compactifies this entire form. ठीक है, it compactifies the entire form. Is that clear or is that not clear? And also understand that we have to write it in a manner, that we get a real solution, because you see x as a function of time and y as a function of time. What does that represent? It represents, you can say that some position of particles, isn't it? It represents position of particles. Physically, if you think, what is x as a function of time and y as a function of time, it tells you that what would be the position of particles which are governed by this coupled differential equation, Okay, so in any case, one should understand that these are real things. So what we'll do a certain trick uh, that will make it real. So what I'll do, I'll take a1 as e की power iota, you can say phi, or you can say phi 1 for that matter, or you take some constant here. So you'll take b1 by 2 a e की power iota phi 1. You take a2 as its complex conjugate, and you'll see why I'm doing that. Okay, a2 is complex conjugate of the same. A3 if you take as b2 by 2 e की power iota by 2, and a4 if you take b2 upon 2 e की power minus iota. Is that clear? मतलब अभी के लिए इतना समझो, यहां तक समझ में आई बात?
हाँ भैया.
Okay, now if you replace all these things up, what you'll get? You'll get b1, and this is 1 comma 1. Okay, this is 1 comma 1. Is b1 को यहां लेके जाओ, let's say इधर. So b1 by 2, ये e की पावर माइनस e की पावर आयोटा phi 1 इससे मल्टीप्लाई होगा, तो ये आएगा e की पावर आयोटा ओमेगा टी प्लस आयोटा phi 1. थोड़ा ध्यान से देखते हैं. So यहाँ पे क्या आएगा? e की पावर आयोटा phi 1 plus omega t, and then there will be e की power, just for instance I'm writing, ठीक है, minus phi 1 plus omega t divided by 2. ऐसे ही सारे जगह पे तुम्हें दिखेगा, ऐसे कुछ टर्म्स दिखेंगे, राइट? सो ये टर्म क्या होता है, खुद सोचो, ये क्या होता है? कॉस नहीं होता? इफ यू अंडरस्टैंड, e की पावर आयोटा थीटा प्लस e की पावर माइनस आयोटा थीटा. कहाँ गए सारे?
हाँ भैया.
ठीक है, थोड़ा ध्यान से देखो. अगर यहाँ पर a2 की जगह तुम b1 by 2 e की पावर माइनस आयोटा 5 लिखोगे, सो ओवरऑल ये टर्म अपने आप नहीं बन जाएगा कॉस के अंदर. सो व्हाट विल गेट, effectively I'll get x and y as some b1 1 comma 1, and then you can write it as cos of omega t plus phi 1. And similarly, the last two bracket can be compactified and written 1 minus 1, and you will get cos 2 omega t plus phi 1. See, again, the same solution. One of the modes is moving with 2 omega, the other mode is oscillating with omega. This is what you've got from the first solution. However, this is quite complicated, but lately you will understand that to always decouple a differential equation by doing a linear combination is not an easy task. It may be a difficult one than this thing. Once you are in practice, you'll be able to do all these steps. So we'll do all kind of problems. Like we're going to do 2 springs, we're going to do 3 springs, probably I'm going to do n springs also if possible. But this is the third methodology that I'm going to follow. So you understand that your x as a function of time, y as a function of time, in a vector form, I can write it as b1, 1, 1, and then I have this cos omega t plus phi 1, and then you have plus b2, 1 minus 1, cos 2 omega t plus phi 2. Is that clear to you? And now also you can see that if I write x plus y, what will I get? I will simply get b1 cos omega t plus phi 1. And if I write x minus y, I will get some b2, and then I will get, I think, x minus y, and this b2 will come out as cos 2 omega t plus phi 2. Is that clear? Or is that not clear? कहाँ चले गए सारे?
एक बार वापस बता दो मुझे, x प्लस वाई और x माइनस वाई।
Okay, ठीक है. So understand the point that this is your x, this is your y. This is b1 cos omega t plus b2 2 cos omega t plus phi 2, and then you have b1 cos omega t plus phi 1, and then you have minus b2 cos 2 omega t plus phi 2, and this is this. So now add x plus y. If you add x plus y, so sorry, there would be some, मतलब ठीक है, x plus y by 2 ले लो, x minus y by 2. So x plus y by 2 would be b1 cos omega t plus phi 1, and x minus y by 2 would be b2 cos 2 omega t plus phi 2. So what you understand is that your linear combination x plus y is oscillating with the frequency omega, and the another linear combination x minus y is oscillating with the frequency 2 omega. Or in other words, you can say that for x plus y to get executed, for x plus y to be executed, your b2 must be equal to 0. देखो ना, अगर इनको ऐड किया तो b2 अपने आप ही 0, मतलब b2 है ही नहीं है, इस तरीके से कुछ हो गया. And for x minus y, so b2 is equal to 0, or I can say that b2 term disappears. I should write not b2 equal to 0, but b2 term disappears, and for x minus 1, your b1 term disappears. Okay, and in order to understand that if even if I write b2 equal to 0, then also things would be like same. So if b2, sorry, if b2 equal to 0, अगर b2 is equal to 0 हो जाएगा, that implies x equal to y. देखो ध्यान से, if b2 equal to 0, then x equal to y for all the times, and both of them oscillate with frequency omega. This is sometimes referred to as symmetric stretching, or you can say symmetric mode. And if b1 equal to 0, then what does it imply? It implies x equal to minus y. This is kind of anti-symmetric. And here it will oscillate with 2. So there are two pure frequencies associated with two different modes, and these two different modes are called, these two different coordinates are called as normal coordinates. These are called as your normal coordinates. These are called as your normal coordinates. Or you can label them by, if you want to label them in, label them by vectors also. Vector would be 1, 1 and 1 minus 1. So 1, 1, this particular vector is, or you can say this normal coordinate is oscillating with frequency omega, and this particular 1 minus 1 is oscillating with the frequency 2 omega. 1 minus 1 means your x is equal to minus 5. That is your, we'll see all these physical interpretation as we go along, but understand this is how you decouple a coupled differential equation. This is the first lesson for the coupled oscillators. Is that clear? I mean, these are the similar methodology we'll see in the Lagrangian formalism also. Don't worry about it. Like similar structure we'll see. I'll not say the similar methodology, but similar structure you will find there also. Is that clear or not clear? So in this lecture, we studied how to decouple a coupled differential equation. I'll meet you in the next lecture for the coupled oscillator case 1, and we are going to complicate it as much as possible in times to come. But today we'll keep it as simple as possible. Is that clear?
हाँ भैया।
बाकी सब मर गए क्या? अल्पना कहाँ है, रजित कहाँ है?
हाँ भैया।
यस सर, क्लियर।
ओके, चलो, धन्यवाद।